Okay, guys, so here we are for the 2.6 day 1 video notes. So let's get started. Hopefully you got this packet. If you didn't, I think you're going to want this packet. It's really pretty handy because you're going to be able to follow easily as to what's coming up and what is next. So you should be able to print it off. If you cannot print it off, then you need to run up to the school and grab one. All right, so we are going to talk about the function domain and range chart. And this is basically all of the parent functions. And so these right over here are your parent functions. And the important things about the parent functions, it's kind of your basic function. So it's important for you to kind of have an idea of what all these look like. When you have a constant is basically a number without a variable. And you'll notice that in the SAT test, they actually use the word constant a lot. If you don't know what that word is, it's going to be a lot harder for you to understand what the question is asking. It's just a number without a variable. So in this case, f of x equals 2. 2 is a constant. So what we look at that, and there's a couple ways to go about this. You can graph it, and I will show you. If I were to go to Desmos, let's go back to Desmos.com, and I went ahead and opened up the graphing calculator and put up the y equals, because f of x we know is y, so we can put y equals 2, and what that looks like, that's just a straight line right across the y-axis. So if we're to draw that, it's right at 2. And our domain, you'll notice our y-x coordinates are going to be all real numbers. So you can say x, these little squiggly brackets is the set of, and you can either write all real numbers. You can write that negative infinity, positive infinity. Here you've got your notation there, your interval notation, and then you've got your inequality notation like this. So all of those are correct. Your range, at this point, the only y value that's even being touched is 2. So y is the set of numbers where y equals 2. So that is... So you can write it like that. You can write it as y equals 2 with the set, or that's probably the way you want to write it, one of those two ways. Linear, so now we've got linear. So if we go back to our Desmos, if we are going to go to y equals x, oops, not y minus x, y equals, there is your basic line function. So if we were to draw that, it's going to go through the origin, the slope of this. This is basically y equals 1x plus 0 if you wrote it into y equals mx plus c form, where your slope is 1 and your y-intercept is 0. But this is your parent function, very important. And so your x, again, is all real numbers, so I'm just going to do negative infinity to infinity. My range also is all real numbers, so negative infinity to infinity, or all real numbers. Okay? Absolute value, again, if you go to your Desmos and you plug in your absolute value of x, absolute value, and that's what it's going to look like, that V shape. So you've got something that looks just like a line, except for you'll notice this part of the lines are exactly the same. This part is this line flipped up, because we know that when you have the absolute value, x cannot be negative. Or, I'm sorry, x can be negative, but y cannot be negative. So as x gets negative, then the y becomes positive. So in this case, your domain, again, is all real numbers, or negative infinity to positive infinity. Your range, however, is going to be the set of numbers where y is greater than or equal to 0, or you can write it like this. Make sure you include your 0, or you can write it as y is greater than or equal to 0. Okay? Quadratic. Again, if you want to go to Desmos and look that up, it's going to be where your vertex is at 0, 0. Oh, and this is actually 0, 0, 2. I want to point that out. And it's a parabola that looks like this. So your domain, again, is all real numbers, because there's no value of x. And keep in mind, these have been all real numbers. All of these have been all real numbers. And the reason is kind of what we talked about up until here. It's all real numbers because there's no square root. We don't have to worry about it being positive. And the x is not in the denominator. So when you if you don't have actual restrictions on your x value, and it is not in a square root, and it is not in the denominator, chances are your domain is going to be all real numbers. Okay? Now my range, again, is the set of numbers where y is greater than or equal to 0. And so I can write that as 0, infinity, or y is greater than or equal to 0. All right. Now we've got this square root. Now there is going to be a problem with my domain. And if I go to my Desmos and I plug in that graph, I'll see that not only is the x always positive, it never comes over into this negative range, but the y is always positive. It never comes into the negative range. So at that point, you're going to notice that your domain is going to be this set of x values where x is greater than or equal to 0, or if you put it in interval notation, 0 to infinity, and that actually includes 0, so I'll put a bracket, or x is greater than or equal to 0. And if it starts at 0, 0, and I graph it like this, and my y is going to be similar. Y is the set of numbers where y is greater than or equal to 0, or 0 to infinity, or y is greater than or equal to 0. So keep in mind, this is when all of a sudden at the square root, there's domain restrictions. And we aren't talking about, we don't have irrational functions where the x is in the denominator. So, and then our cubic equation is going to look, if you don't already know that, let's look at that and see what that looks like. This would be x to the third power. Let me see how to raise it. I think if I do that and I go back over here and pop 3 in there. And that is the cubic parent function. So if I come back to my drawings, it looks like that. So again, my x is all real numbers because x is not under square root and it is not in the denominator. My y in this case is also all real numbers, so negative infinity to infinity. right, so here's where the fun really begins. If you flip your page, you'll notice that here we've got some functions exploration. We've got an equation here, we've got a table here, and we've got a graph here. And so the goal is basically to go from the equation to the table to the graph. But what I also want you to be able to do is to be able to eventually go from the equation to the graph without writing the table. Now, it's important for you to know how to get from the equation to the table. So this is a very important step, and so don't skip out on that step. So let's talk about this. So when we go from the equation, here's my equation, to the table, this is my x values, these are my y values, right? So the function of x squared, I'm basically just going to say, okay, f of negative 4, if I plug negative 4 into x squared, so I get 4 squared, that is going to give me 16. Do you see that? Negative 4 squared is 16. So f of negative 4 equals negative 4 squared. I'm just putting the x in here and getting 16. So if I just do that for every value, negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. You know how this goes. So we get all of these, this table, and then you're going to 16, then you're going to plot these points. So you would go over to negative 4, 1, 2, 3, 4, and you'd go up 16, which is off the graph, and you'd plot that point. And then you'd go over 3, 1, 2, 3, you'd go up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and here's that. Over 2, up 4, 1, 1, 0, 0, 1, 1, 2, 4, 3, 9, and then there you have your graph, okay? So hopefully you can do that. Now here's where it starts to get kind of a little bit more interesting, because if you go ahead and plug this in and say, okay, f of, oh, I'm going to not have enough room, f of negative 4 equals negative 4 squared plus 3, well, 16 plus 3 is going to give you 19, okay? Now I've already done these x squared, so I can just go ahead and take these values as my x squared and add 3. So this would be 9 plus 3, which is 12. This would be 4 plus 3, which is 7. Hopefully you guys are seeing where I'm getting this, because these are the same, and then I'm adding 3. 1 plus 3 is 4, 3, 4, 7, 12, 19. And if you don't see where I'm getting this, I'm just taking these numbers and adding this 3. Now I can again go to my graph, and instead of going to 0, 0, I'm actually going to 0, 3, which is going to be up 3. 1, 2, 3. And 1, 4, negative 1, 4, 2, 7, so 5, 6, 7, and so on. And you're going to notice that this has moved up 3 units. And look at here, it's up 3 units. So go ahead and try and work the graphs on all of these and see what you get. That'll be on the next video.